And I guess now we have, in a minute, we'll start a question and answer session for all three speakers this evening. So maybe all the speakers can join now. Yeah, I think everyone is here. Right, so we can start the discussion. Actually, concerning this comment Dmitry just made about continuous spectrum of operators in the celestial CFT, maybe Glenn and Xavier have comments on this. So it doesn't look like a conventional, say, two-dimensional CFT that we typically have. Well, I guess we can. I mean, there are CFTs which have continuous spectrum of primary fields, right? But do you have any comments on this?
No relevant smart comment on this, not really from my side. Sorry about that. I mean,
no, just a buzzword. I would buy that it would be a conformal Carroll CFT. I mean, conformal Carolian CFT, but whatever that means.
Mm-hmm. And also concerning flat space, something like flat space holography, people do sometimes talk about this NS5 brane holography with linear dilaton, which is not like ADS, but then in the boundary theory is little string theory, which is inherently non-local. So, I mean, there could be some generalizations of ADS holography to these other cases, but they're certainly don't involve typically a local field theory on the boundary. I'm not sure if people consider those cases as from the point of view of group theory, like you did.
That would be interesting.
Yeah, for example, this two-dimensional string theory where you have a matrix model, the large N quantum mechanics, which is dual to the theory with the linear dilaton, and I mean that has been studied a lot very concretely, but it's certainly not like ADS holography.
well, all I can say, which is not directly relevant, is that if you do in 3 dimensions, and you start from this Chern-Simons formulation, which is of course not the holography you have in mind, but still, and you look what happens on the boundary, what you find for flat space cavity is an ISO 2-1 chiral Wessumino-Witten model, and then also a kind of Liouville theory, which is also chiral, just chiral bosons, which have BMS3 symmetry that you can find. And they have a strange dependence on U, linear dependence. And I mean, you can construct them exactly like you do Liouville theory from Chern-Simons theory, but okay, that's not probably the kind of holography you have in mind. That's just this gravitational boundary version.
I guess one concrete question is if there is any example of celestial sphere holography where you have a known CFT which you can study by itself and which can be compared with flat space gravity. I guess that does not exist, right?
I don't think, not yet at least. Yeah.
Yes. Questions or comments, please? Yes, Zhenya, do you have a comment?
Yes, so, well, no, I actually have a question.
helpful because usually people have comments. So Xavier, you showed us plenty of flat space singleton candidates. And the obvious question, yeah, two, but the obvious question would be, well, did you take the tensor product to see some continuum of states, maybe interesting ones?
It's a good question. Of course, it's something we want to do. To be sincere, maybe it even exists in the literature. We discussed that with Blaja, but it not yet came out with concrete. So I have nothing to say, except that personally, I'm not too optimistic. I would be very surprised if you have a discrete sum like we have. Because if you think just about since they are also Poincaré representation, if you just multiply 2 Messless scalar, as far as I know, you will get a continuous tau. So, no, flat space holography really seems to be tricky. It's a good question, yes. Yeah, it's something we want to do. Yes, yes.
Okay, many thanks.
Maybe I can ask a question to other speakers. So
yes.
I was wondering, so to me it looks like BMS and Poincaré, well, they have a common part, but still they're different. And what about representation theory? So, well, as I understand, it's a bit different, right? And what do you do with the mismatch? How do you interpret this?
So, yeah. Maybe Glenn?
No, I want to pass the ball to you, of course, but well, you know, I showed you in detail one representation, which is not the one you're interested in, which is the quad joint, and you really can exactly see the mismatch.
Well,
exactly.
Just for history, by the way, I should have credited you because the Sachs representation, just for the history, maybe people are not interested, but it was Glenn who showed me many years ago, in a book by Moshe Carmeli, exactly. But actually, I noticed recently with Blaja that it's just the Sachs.
I didn't know. Well, I have.
It's a bit overlooked for some funny reason. On my point of view, I think it's a subject that is not been sufficiently maybe studied, BMS representation theory.
Well, even people doubt even this McCarthy work on unitary irreducible representations of the BMS because they say it depends on the topology. There has been that you put on this infinite dimensional abelian part in order to apply this induced representation theorem. And so there has been a paper by Italians about that, where they say, because the success that people claimed for the BMS representation, at least McCarthy, was that there were no continuous spin representations, contrary to what happens for the Poincaré. And then somebody told me that the status is not at all clear, so I cannot, so let me just throw that out.
No, but it did, because actually also discussing with Blaja, we went through the whole series of paper by McCarthy, and actually he changed his mind in some sense.
Yeah. And it depends, you know, because this
McCarthy,
because this abelian factor is infinite dimensional, and the standard tools that you get from the book by Raka and Barut, so they don't apply exactly to this situation. So you have to do something. And, so I'm not even sure that this is all completely understood, but I'm not the expert on that.
Yeah. So maybe one word for the audience. So what we are discussing is that so you have the super translations are like the algebra of functions on the sphere. But then when you do the representation theory, the momenta, that you do the Wigner type of classification, you will consider the momenta. And these ones, they are, of course, the dual of these functions. So they are, strictly speaking, they are distributions. And so that's where things start. And indeed, in the first papers, McCarthy considered the Fréchet space, maybe something like this, very fancy. But then later on, he discussed more genuine distributions, and then he could get different results, which are more in the idea that Poincaré lift, the ER of Poincaré lift to BMS, all of them.
Can I comment something?
Yeah, and
Yeah, please.
Yes,
Sure.
better. Yes, yes, please.
About these different representations of BMS, was an old paper by Longhi and Materassi, where they were considering a free scalar field and found a representation of BMS in terms of Fourier modes. Therefore, I don't know how could be the relation with other representation, but there's an explicit form of these representations. And more recently, with some student, we have seen this in the case of BMS3. And also from this point of view, I would like to ask a question that the higher spin symmetries, it comes from the closure of the conformal group being nonlinear, but in these papers by Longhi, they were finding a non-local transformation that was linear on the fields and the momenta that were giving BMS. Therefore, it seems that there are two sources of getting BMS. As the enveloping algebra of the conformal group, I mean, of the D'Alembertian equation, or in this Longhi Materassi way as a non-local transformation of the fields. Somebody has some question or some comments, sorry about that?
Yeah, I will look at this paper. I didn't know about them, so I cannot comment. But yeah, sure, I will look. Thank you.
Maybe to back up the remark that I was making on, can you see my screen? So this is the paper where they discuss these issues of continuous spin representation or not, if you want. And it has to do so. Okay, Dimitri, if this is what you were asking, so this is the kind of question and the kind of papers I think one should look at. But it's all very old already, but okay. But it seems to me, with respect to what you are saying, Xavier, if you use this spin-weighted spherical harmonics, the dual space and the space itself, you suddenly have the same type of expansions. So then you do not have anymore this distribution issue that one is bigger than the other or something like that. So maybe that's a way to go, but then you have to look at completions. So maybe that's a good way to control them, which is a balanced way of having the same, you know.
Yeah, that's right. I see what you mean. Okay, maybe, yeah, maybe.
Since we have experts here, there is recently a big wave of activity on this celestial holography. So maybe, yeah, I haven't so much kept track of it. What is the main focus now in this wave?
Okay, I'm not enough an expert to be able to answer. I guess one of the things, first people were, part of the activity is how the representation, the Lorentz representations look like from the point of view of sky, that was, and from the point of view of scattering between sky plus and sky minus. And then where BMS came in is a bit like in conformal field theory, where you ask that maybe this larger symmetry group is going to constrain your scattering amplitudes, even though it's a larger group than, so you do linearized spin 2 scattering there, and you ask if this constrains the amplitudes. Okay, I mean,
so it's somehow focusing on describing flat space S matrix from the point of view of celestial CFT.
Yeah, I think it's yeah, what you can say when you look at spin 2 scattering amplitudes, really, when you look at them really from the point of view of between Sky plus and Sky minus, when you transpose everything there and adapt everything to that, what kind of representations are useful, what are the constraints when you see it there. There seems to be some very nice simplification coming when you do this kind of things. But then there is always the question, is it flat space and spin 2 on flat space, or do you have black holes? Do you go beyond flat space, in what sense, or not? Do you really have scattering with black holes inside? But okay, I don't think in this session there was really an expert on celestial amplitudes, but it has become a business on its own. Yeah.
Yes, this hasn't come up yet, but what about the sitter holography? Then the situation is kind of simpler, right? At least for higher spin theories. But, are there any comments on that?
It's for Yasha Neyman, if he's around, maybe, but.
Let's see. I don't think he's in the room. But in that case, there is no problem on the level of group theory, right?
In principle, it's much simpler because indeed, since the dual theory need not be unitary.
Right. Well, there are known cases where we know it's not unitary, but.
So yeah. So in this sense, yes, many things go more smoothly. But really about the genuine subtleties, I think Yasha is one much more expert.
Any more comments or questions for speakers? I guess it's been a long day, so maybe we'll just wrap up the discussion and thank all the speakers from the evening session.
Thank you.
Thank you very much.
Thank you very much.